Good day, everyone. I am Mark Joseph J. Toledo, the presenter of paper number 166, entitled Flood Levels and Trash Detection, Integrating Sensors with Support Vector Machine and YOLOv8. I am from Mapua University, Philippines. This presentation is for the I2CACIS 2025. Here are the authors of the study. I am Mark Joseph J. Toledo. Together with me is Kenchi M. Ramos and Engineer Phoebus Ridge G. Cruz. Let's now start the introduction. Due to Philippines' poor drainage infrastructure and vulnerable geographical location, the Philippines remain one of the most flood-prone nations globally. Floods claim over 100 lives annually and severely affect rural communities lacking access to early warning systems. Early flood detection plays a crucial role in reducing casualties and damage. By integrating AI with weather monitoring, river gauges, and rainfall forecasts, we can build a smarter, real-time flood monitoring system. Despite recent advances in flood detection systems, critical gaps remain. Most existing systems focus solely on water levels and lack pH monitoring, which is essential for detecting water contamination. They also fail to incorporate AI-based trash detection, limiting the ability to assess waste buildup that can worsen flooding. Additionally, sensor reliability and coverage in rural areas remain a challenge. The general objective of this research is to design and implement an integrated early flood detection system using sensor data and AI-driven image processing for real-time and accurate flood assessment. Specifically, it aims to, first, develop a system using ultrasonic, water level, rain and flow rate sensors. Second, calibrate sensors and optimize image processing with CNN and SVM for detecting water levels, pH, flow rate, and trash. Third, test the system's efficiency and identify potential errors. Fourth, validate the system's accuracy by conducting tests in Quirino, Manila, Philippines, and comparing the results with past studies. For our related studies, previous studies on flood detection systems have primarily focused on sensor technologies, image processing, and early warning mechanisms. In 2022, a wireless sensor network using LoRaWAN and Z-score normalization was developed to improve water level detection accuracy. In 2023, another system integrated rain gauges, flow meters, and image recognition via Raspberry Pi to trigger a 3-stage alarm. However, most systems lack capabilities like trash detection and real-time image-based analysis. Our research addresses this gap by incorporating convolutional neural networks for accurate flood level assessment and trash identification, enhancing both precision and environmental monitoring. Our flood and trash monitoring system operates through 3 main stages: input, processing, and output. At the input stage, it gathers sensors data, water level, rainfall, flow rate, and pH and image data for trash detection. In the processing stage, data is analyzed using AI models like CNN and SVM to classify objects in floodwater as trash or non-trash. The output stage uses GUI and an LCD to display real-time sensor reading and alerts. This is the schematic diagram of our system, and the right is the prototype design. The system pairs an Arduino Nano with 5 key sensors: ultrasonic, flow rate meter, rain gauge, water flow sensor, and the pH probe to capture real-time flood data. The Arduino Nano streams these readings to a Raspberry Pi 5, which also drives an attached camera for trash detection. It is powered by a 5-volt power bank. The Raspberry Pi analyzes everything and pushes results to both on-site LCD and a laptop-based GUI. This portable, remotely accessible setup supports quick decision, increasing flood response and environmental monitoring in one integrated package. This is the front and rear view of our prototype. This flood and trash detection system prototype measures 12 by 12 by 16 centimeters and is designed for vertical mounting on surface like wooden or metal posts. The GUI is divided into key sections for efficient monitoring. On the far left, it displays real-time sensor reading and system status. On the right, it shows alerts and analysis, highlighting the threshold breaches like abnormal pH levels to quickly notify users. At the bottom, the interface includes MQTT settings with testmosquito.org as the default broker. Here's the main process of the system. The system activates when rain and water level sensors detect potential flooding. These sensors continuously monitor conditions, and if no threshold is met, the system loops and keeps checking. Once threshold is reached, the sensors are turned off to save power, and an initial alert is sent. Then all the remaining sensors take over for detailed monitoring, measuring water level, flow rate, and water quality. If flood conditions are confirmed, a second alert is issued. If not, the system stays in monitoring mode, ready to respond. This is the actual testing setup of the flood and trash detection system, mounted on a wooden stand or any pole and enclosed in a weatherproof casing. A visible camera uses the YOLO algorithm to detect trash in flood waters, while water level and pH sensor monitors water height and quality. Testing is conducted at night, using street lights to improve camera visibility in low light conditions. This setup allows for real-time data collections and accurate evaluation of systems performance in detecting both flooding and trash. Let's now move on to our results and discussion. The flood detection prototype was tested for accuracy in measuring water height and pH levels. A measuring tape verified the ultrasonic sensor, and the pH strips were used to compare with sensor readings. Water levels from 5 cm to 30 cm showed 0% deviation, while a slight 33.33% deviation occurred at 3 cm due to ultrasonic limitations at short range. pH tests at levels 2, 4, and 7 showed a perfect match when rounded, confirming the sensor's precision despite the test strips giving only whole numbers. Overall, the systems accurately monitor both flood levels and water quality. For the next testing, the flood monitoring system was tested in sunny, rainy, and nighttime conditions to assess sensor and trash detection accuracy. It achieved 91.67% sensor accuracy and 83.40% trash detection in sunny weather, showing stable performance. In rainy conditions, sensor accuracy reached 100%, but trash detection dropped to 74.62% due to water reflections. At night, sensor accuracy remained at 91.67%, while trash detection fell to 69.38% due to low light. This result shows strong sensor performance across conditions but highlight the need to improve trash detection under rain and low light environments. Over the 5 days, the flood monitoring system was evaluated based on water level accuracy, rain detection, pH detection, and trash detection. Water level and pH detection consistently showed high accuracy, reaching 100% from day 2 onwards. Rain detection is also remained effective. However, trash detection varied starting at 60% on day 1 due to false positives and peaking at 75% on day 3. Despite some improvements, accuracy declined again by day 5 to 66.67%, indicating ongoing challenges in distinguishing trash from non-trash. Overall, the system performed reliably, while trash detection need further refinement. The flush detection system monitored water level, flow rate, pH, and trash presence across several dates. On March 30 and similar days, water level rose slightly with no flow and minimal trash, showing light rain impact. On April 5, heavier rainfall led to a sharp rise in water level, slight flow, and more trash detected, triggering flood and pH alerts due to runoffs. On April 16, 21, and 25, Water level increased without flow, indicating stagnant water. Overall, the system effectively responded to verifying rain intensities, accurately issuing flood and pH alerts in real time. This table summarizes 5 days of testing for flood detection and trash classification system. Each day, the system was evaluated based on sensor accuracy covering water level, pH, and rain detection, and trash image classification. For example, on day 1, 3 out of 5 trash images were correctly identified, giving 60% accuracy, while sensor readings averaged 93.33%. Overall systems accuracy was calculated by averaging sensors and trash detection performance. By day 2, perfect sensor accuracy improved trash classification, raised the overall accuracy to 86.67%, showing progress in areas for further refinement. This table shows the flood detection system's performance over 5 days, where it consistently issued accurate flood alerts. Each day, the system correctly identified flood levels ranging from low to moderate, with 100% alert accuracy. For example, on day 1, a gradual water level rise triggered a low flood alert, allowing early response. On day 2, it correctly classified moderate flooding. The system's ability to detect subtle changes using real-time sensor data highlights its reliability and sensitivity, making it effective for continuous flood monitoring and timely alerts. This last table highlights the flood detection system's performance during a 40-minute heavy rainfall event. Water level rose from 7 to 14 centimeters, while the pH remained consistently at 4, triggering pH alerts for potential contamination. Trash detection increased from 5 to 15 items, and the systems issued flood alerts at every interval, showing high sensitivity to environmental changes. This consistent monitoring and timely alerting demonstrate the system's effectiveness in detecting flood risks and water quality threats, enabling faster response and improved disaster preparedness. For our conclusion, this study developed a real-time flood and garbage detection system using sensors and AI to monitor environmental hazards. Over 5 days, the system reliably tracked water level and pH with 100% accuracy from day 2 onwards, proving effective in monitoring flood conditions and water contaminations. However, garbage detection showed inconsistent accuracy ranging from 60% to 82%, mainly due to false positives caused by poor weather and visual obstructions. While the system shows strong potential for flood and water quality monitoring, improvements are needed in trash detection, especially in challenging conditions. Enhancing AI models and sensor calibration could boost accuracy and make the system more viable for real-world disaster management. Here's our video demonstration for our flood levels and trash detection system. First thing that we need to do is to connect the system to the internet. Next is we connect the GUI to the system, which is in the laptop. After that, we can go outside and test the system. Here's the actual testing setup in action, where we can see the 3 sensors soaked underwater, and we can see that the LCD and the remaining sensors are above, enclosed in a weatherproof case. Lastly, here are our references. That is all for our presentation. Thank you for listening.